morning. I'm Doshi Velez, and I'm going to be starting a three-part series on reinforcement learning. So just to give you a little bit of an overview of how we're going to do this. So this set of lectures is going to show you some of the motivation and also some of the core fundamentals of reinforcement learning. And then at the second session, we're going to be playing around with some really basic machine learning algorithms and seeing how different parameters affect performance. So make sure you bring your laptop or you can buddy up for that second lecture. And then the third one, we'll talk about kind of new and future directions in terms of reinforcement learning, what people are doing today. So I want to start out with motivation, some videos. These are not my videos, but videos that you may or may not have seen before of things that have been accomplished by using reinforcement learning methods. And we're going to peel them back and talk about what are the core things that had to be accomplished, right? What was hard and what had to be accomplished to make these sort of achievements possible. So I'm sure that many of you are familiar with AlphaGo, beating the first time a real game has been won by an AI. We'll talk about how that was possible. Before that, you've probably seen Atari being played. So here is Pong, where you have the agent moving fast and able to control the ball well. A little bit earlier on, and I just want to give you a flavor, right? And then we're going to go into the essentials. So we also have autonomous helicopter flight. So now this isn't a video game or board game or game of any kind. This is an actual helicopter. It's doing all sorts of stunts in the air. Stunts that are very, very hard for people to do and to program in. So how is that possible using reinforcement learning and similar techniques? And then we have more mundane tasks, like flipping pancakes. So you see this in the middle of the circle, right? So you see it go forward, and again, I'm just skimming through a lot of videos just to give you a sense of like cool things that reinforcement learning can do. Thanks to myself, I flipped some pancakes. Very cool. Forming knots, again, very difficult task. Hard for robots to do in terms of manipulation. That one takes a little longer. And then this looks very simple, but it's going to be about as close to real world as we get in terms of explaining how we actually solve these problems. This is a pole balancing task. The robot is trying to balance the pole. So here are a bunch of, again, fun videos. We're going to talk about the basics. These are from labs all over. My research happens to be more in the healthcare domain, where we're using reinforcement learning to identify what treatments are best for what patients. So there aren't really videos involved. It's still very important. I'll tell you more about that at the end. So I'm going to turn off the projector and the rest I will do it. Ready for work. Alright, so the core question in reinforcement learning is how to make decisions under uncertainty. I'm going to give you a motivating example. You saw all sorts of flashy things, but one that I experience on a regular basis is how do I get to work in the morning? Okay, so let's say I'm here. This is my house. Here's work, right? And I can take a path that looks something like this to get to work, walking. Or I can walk some other way to get to work, right? Or I can walk just a little bit, and then I can take a bus. Or I can walk a little bit backwards, right? Which might seem like a strange thing to do. But then I can take the subway. subway train, right? And so I'm trying to figure out what's the best thing to do. And so what are things that make this problem interesting or challenging, right? So one thing that is somewhat challenging about this problem is that well, obviously I've built up some experience, but the real way for me to collect data on this question, very mundane question, but we deal with these sorts of mundane questions every day when we make decisions, is that I only know the outcome after I try it, right? If I'm like, oh, maybe I can take this alternate street to get to work, I won't know whether that's a good idea or not unless I try it, right? So the key aspects of reinforcement learning is that we have to learn from experience. And this is what distinguishes it from a very closely related field, which is planning. So if you had a model and you could simulate exactly how long this path would take versus this path would take, then perhaps you've got that part down and you can just solve it, right? So this is different from planning. Although we'll talk a bit about planning today. Right, so that's one key thing that makes it hard. Another thing that makes this question interesting or hard is that there's a sequential set of decisions that are being made, right? And the way I drew it, it doesn't necessarily look that way. But when I leave the house, I'm walking, and then I choose to keep walking, and I choose to keep walking, and at every instant in time, I'm making a decision, right, to keep walking if I'm going on this route. And suppose that route turns out to be a really bad idea, and I show up massively late to work, and it's a disaster, right? What do I blame, right? Is it the fact that I was walking at some speed over here, or over here, or was it the first decision to start on this route in the first place, right? So there's a question of delayed reward, or what is this temporal credit assignment? Or I should say, challenges over here. So these sorts of sequential decision-making problems, actions can have long-standing effects, and we have to figure out what's the right thing to do. And you could say over here, maybe leaving the house this way was a bad idea. If you look at this route over here that involved going backwards, right? Initially, that might look like a bad idea, right? Like I'm walking away from my workplace. But if the subway is really fast, overall, it turns out to be a good idea. So again, here's an example of a decision that looks locally suboptimal if I'm using a proxy of like how far away am I, right, at what time. But turns out could be extremely optimal. So again, there's this question of delayed rewards. How do you assign credit? Another really key question is exploration versus exploitation. Because we're only learning from experience, right, we have this dilemma, right, that I perhaps do not have the luxury to just be late to work for a long set of months. And then I sort it out, and I'm like, okay, now I know the optimal way. And by that time, the seasons have changed, the subway line has changed, and it's not useful anyway, right? So there's this idea that you want to do well all the time, right? There's not this notion of like practice and then success, like training and test as two separate categories. It is all test time. And so the question is, how can we, over the long run, accumulate large amounts of reward? And to solve that, we have to be able to balance doing well with what we know now and learning more about our environment. So we have to figure out what's the right trade-off to learn something that might get us more in the future versus just take advantage of what we got now. And the final one, and this one is general to all of machine learning, and one that we'll touch on probably in the third lecture, and that's a question of generalization. So in this lecture, we're going to focus on very simple domains. We're not really going to worry about this particular question. But as soon as domains get more complicated, there is this question of what can I take from this very simple example of getting to work, and now if I need to get to a doctor's appointment, are there pieces of this that I have learned that I can apply to a new problem, right? So there's that transfer, and there's also, do I have to learn that going forward over here does the same thing as going forward over here, does the same thing as going forward over here? Like, when can I learn that walking is walking, right? So there's all sorts of level of transfer and generalization here that is critical to real problems. But we're not going to talk about that again until that third lecture. So what I'm going to start out with is, so today is going to be mostly talking about delayed reward, and we'll touch on exploitation versus exploration. And learning from experience will be the whole way through. Okay. So roughly this is going to be lecture 1, lecture/practical 2, and lecture 3 is how we're going to look at these 3 major challenges for reinforcement learning. So to be able to talk about this, I'm going to give you a very basic framework. And this is the same framework that's used in all of these modern RL applications that you saw the tiny videos of. And the one point that I want to take away, or start out with, is that there's been a lot of advances in RL that I think have come from a lot of core work in representation learning, right? The generalization problem. That we had tools that were good for working with relatively small spaces, and as we learned how to do generalization better, for example, with deep networks, we're able to solve problems that weren't necessarily possible before. Right? But the core questions have not changed. And so even though the examples today are going to be very simple, you're still going to, it doesn't matter what your representation is, right? These questions are still going to come up because you still have exploration, exploitation issues. You still have delayed credit assignment issues. Doesn't matter what your representation is. Right? So that's why we're going to do very simple problems today. But I just want to emphasize that these are still questions. Doesn't matter how you, what problem you're solving, that any reinforcement learning problem will have. Right. So the core framework that we're going to assume is the following. We're going to assume that we have an agent, and there's multi-agent versions as well, but for now let's keep it at one agent. And the agent is going to send actions to the environment. And the environment is going to send back 2 things. The first thing that the environment is going to send back are observations, so some set of measurements. And the other thing that the environment is going to send back is some notion of local reward. And this reward, it might be the reward of, for example, if you're walking, you might be getting more tired, right? So that's an example of a reward that comes back after every action. But then when you finally get there on time, then you feel good. And that might be a large reward, right? So the rewards are local. And the idea here is that instead of telling the agent exactly how to behave, you're telling it kind of, here are the costs of various different choices locally, and you figure out what's the right course of action to optimize your overall rewards. So let's make that part a little bit more explicit. So the goal, in our case, again, there's robust versions and all these other things, is maximize long-term expected reward. So this can be up to some time. So we just want to take the expectation of all the rewards we're going to collect, and we're told that the game ends at a particular time t. Right? So that's one version of this objective. Another version of this objective, and and the one that I'm going to use for most part today, is saying that, well, let's assume that time just goes to infinity. And I want to optimize some discounted set of rewards. So gamma in 0, 1. So what we have here is we're saying that rewards that happen soon are worth more than rewards that happen later. Right? It is exponential thing. And the only reason why we do this particular form of discounting is that it's computationally convenient, right? It's memoryless. That anytime you start, you can always just say that there's an exponential drop-off. We're going to use that today for convenience. There's also many other versions that you can use. So here's the problem that we're trying to solve. Here's the goal. And now I just want to introduce a couple of key terms. So we've already defined actions, observations, and rewards. So then another key piece of terminology for RL. The first one is the history. And so the history up to a time t is just everything that the agent has experienced. So we start out with some, for example, what if there was some action? Maybe let's start out with a measurement. So we took some measurement, we took some action, we received some reward, then and also some new observation. We take the next one, et cetera, et cetera. This thing, I'll use H to represent the history, represents everything the agent has seen up till some time t, wherever we're sitting right now. That's really big. But in theory, to make a future decision, you might need to know everything that you did in the past, right? Like for example, if I'm sitting at an intersection and I need to know whether to go left or right, maybe it matters if I don't happen to know where I am, right? If I don't have a GPS, then I needed to know what sequence of lefts and rights I made to get to that intersection to know what future step I need to take, right? So I need to remember everything about my past. But as I said, that's kind of inconvenient. So then the next key term that I want to define is this word state. Okay? And this is a kind of overloaded word, and I'm going to try to be very careful about how I use it in the reinforcement learning context. So I'm going to define the state, or whenever I use the state, and this is a definition for it. Whenever I say the word state, what I mean is a sufficient statistic for the history. And what that means in terms of math is it's saying that the probability of some future observation t plus 1, some reward t plus 1, given the state at time t, is equal to the probability of that observation t plus 1 and the reward t plus 1 given everything. So observation 0, 0, R 0, all the way out to so given the state, the future is independent of the past. So in that example of going to work, if I did have my location, right? If I did have those geo-coordinates of exactly where I was, then maybe it doesn't matter how I got there. And depending on the application, that might be different things. So if you started here, you took some path, you arrived over here, here's the goal that you're trying to get to. Well, maybe it's good enough to know just your location, right? But maybe there's another scenario in which maybe you need to know about your location and how much fuel you have left in your car. There's all sorts of things you could imagine having to append. Whatever you have to append, that is the state. So another way to think of the state is a statistic. This is going to render renders our system Markovian. But if we know this thing, then we don't need to remember anything about the past. So it could be, again, very complicated thing. And what we'll talk about on the third lecture is ways to create this state. So for this lecture, we're going to assume a slightly simplified version of this formulation in which we are given this state. So the environment is somehow kind to us. So for this lecture, the environment is going to send us a state. So we don't have to do the work to figure out what's a sufficient statistic. We're just going to assume that if we're given, the environment tells us everything we need to know about the past. So for example, it gives us our location coordinates. Any questions so far? This is all the key terminology we got. Yep.
So the action at time t, is it part of the state or?
So the action at time t, oh, thank you, here. Yeah, condition on, right, this is already there. So it's not part of the state. Right. So given everything you know about the past and the current action, you can make conditions about it. Thank you.
When you say like the state contains enough of the history to be sufficient to know the future, does that mean like enough to know how much your reward is? Is that what we want to know?
But it captures all the information you need to make any decisions. So I see. Are you asking that? Does it also remember all the cumulative?
No, I mean, does it have enough information for me to decide what the value of the reward is for the next step?
So the reward function, we're going to assume that is given, right? So I'll formalize this into a model in just a few minutes, into a Markov decision process. So the reward is going to be a function of the state. So we'll assume that it's a function of the state. And that's not a hard assumption to make because the state is a sufficient statistic for the system. So it's equivalent to state.
Could you possibly write it larger?
Sure. Yeah. Right. Okay. All right. One last piece of key terminology, and then I'll erase and write everything bigger. So the last key piece of terminology is this notion of policy. So which I'm going to, and again, I'm putting this all up mostly so we can get the lettering right, and then everything else will make sense. These are not hard concepts. So policy that I'll write is pi of s, which is a mapping from states to actions. So this is the part that we're going to try to optimize or evaluate. This is our decision-making thing, right? So this is the thing that we decide. We don't have any control over what the environment does. So the policy lives with the agent. The agent has a pi of s inside, and we're trying to design that pi of s in order to maximize this overall loss. So let's formalize this problem, and now what we're going to do is first write down a formal model for the problem. Then we'll talk about how to evaluate a policy. Then we'll talk about how to optimize a policy. Okay. And when we evaluate a policy or optimize a policy, the key question, again, the key challenge that we're going to be talking about in this lecture is this issue of long-term credit assignment or delayed rewards, right? So we need to find a policy. We need to be able to find a policy that will maximize those long-term rewards. Okay. Cool. So let's formalize what I cartooned before. Is that big enough? Raise your hand if it's not big enough. Still a little bit. Okay. So Markov decision process is a picture, or is exactly what we've talked about before. So here we have this a tuple defined by a transition function, probability of next state given current state in action, a reward that you get for taking a state, a certain action in a certain state, and perhaps ending up in a particular state. and the discount factor gamma. And this one might seem unimportant, but we're going to do a little exercise in just a few moments to see how this part actually does make sense. So given a policy, so given some pi of s to a, one thing that I just want us to note is that this thing describes the Markov chain together with our policy. For example, if I have a little world where here I am inside and here I am outside, and I have two choices of actions. If I stay, I come right back where I am, right? And then I have an action which is move, but maybe there's some laziness or inertia, and don't actually move. And likewise, we have something that looks like this for move. And maybe there's some rewards that are only associated with the states, right? Like maybe it's just beautiful and it's nice to be outside and not so, kind of neutral to be inside, right? So here's a picture of an MDP, right, with some gamma. So here's an MDP, right? And the thing that makes this an MDP is that each node